Hi. In the previous video, we started discussing Samuelson Multiplier-Acceleration introduction model. Now, we've discussed, defined the points of the model, we explained all the equations in the model, and finally we were able to condense the model into one single equation, which we said could be estimated econometrically, in the sense that we could estimate the structure or parameters of the model. And finally, what we did was that we found intertemporal equilibrium and economic, so equilibrium in intertemporal sense and in the economic sense, right? We found that this is simply equal to into government spending times the multiplier. Okay, so one thing we haven't done in the previous video was to find the complementary function. And look, this is what we're going to do now. In this case, situation is not as clear as in the, let's just say, regular Keynesian national income model, because we have a lot of different possible cases that can take place here. Okay, and look, we need to start distinguishing between those cases, and depending on the relative value of the parameters, in this case, you will see that this is, of course, gamma and alpha, so NPC, marginal propensity to consume, and accelerator, will actually determine how will the complementary function look like. Okay, let's start slow. We know that in equation we are examining, A1 is -1 plus alpha times gamma, right? And this means that A1 squared is simply 1 plus alpha squared gamma squared. And because A2 is equal to alpha times gamma, for A2 is equal to 4 alpha gamma. Okay, and look, the first thing we want to discuss is when will we have distinct, when we will have repeated roots, and when we will have complex roots. And look, this of course depends on whether A1 squared is bigger, smaller, or equal to 4A2. Of course, if this would be the case, we would have distinct roots. If this would be the case, we would have repeated roots. And finally, if this would be the case, we would have complex roots. Okay, so look, what we need to do right now is to distinguish between these three cases. However, as it turns out, in cases like that, the easiest way to do it is to approach it graphically. But let's start slowly. So look, let's substitute for A1 squared and for A2. So we've got 1 plus alpha squared delta squared, and let's consider the middle case, so equality. This will actually divide the area we will be analyzing into complex and distinct part, and the line we're going to derive over here is going to give us, of course, repeated roots, right? Because in case of repeated roots, this holds. Oh, look, right away we see that two deltas are canceling each other out. There is no minus, right? Over here. It's impossible for gamma to be negative, right? Because it's between 0 and 1. So actually, if we divide both sides by gamma, inequalities didn't change. And now, if I'm going to divide both sides by 1 plus alpha squared, which is also always positive, I'm going to get a function that expresses gamma in terms of alpha. And look, because we have not divided here anywhere by zero, by a negative number, inequality signs do not change their direction. So remember, if this is bigger, then we will have distinct roots, smaller repeated roots. And look, this actually also tells us that once we've got this function down, we will be able to actually distinguish between these three cases. However, drawing this particular function is a little bit troublesome, right? So why don't we just use what we know in order to draw it? Look, if we wanna draw any function, all we gotta do is to calculate the derivative, and based on that we know when they're going up, when they're going down, when they have maximum, minimum, inflection points, and all sorts of stuff. So, what I want to do now is to simply calculate the first derivative of gamma with respect to alpha. And of course, look, this is a quotient. We need to use a quotient rule, right? So, in the denominator, we will have 1 plus alpha squared to the power of 2 to the power of 4. And now, derivative of the first expression times the expression in the bottom minus first expression times the derivative of this expression in the bottom, right? So we will have here, out of here, 2 goes up front, right? And we have 1 plus alpha. Here we use the G. Okay, this is 4 plus 8 alpha plus 4 alpha squared minus 8 alpha minus 8 alpha squared, all divided by 1 plus alpha to the power of 4. Now look, we clearly see that those two expressions are cancelling each other out. Right? Now, all we gotta do is to subtract those, and we get that this is 4 minus 4 alpha squared, right? Over 1 plus alpha to the power of 4, and this is equal to 4 times 1 minus alpha squared over 1 plus alpha to the power of 4. And now look, we equalize this with 0, right? We equalize this derivative with 0. And what we are getting? Like, look, definitely we know that this can never be 0, right? It is always positive. All we need to do is to find a case where 4 times 1 minus alpha squared is equal to 0, right? However, out of this we would get two answers, right? Alpha equal to 1 and alpha equal to negative. But we should remember that under the assumption of our model, alpha is an accelerator. Accelerator must be positive. So based on these two, we find that alpha must be equal to 1. Okay, and look, this is actually already telling us a lot. Why? Look, let me put this on the graph. Here we will have alpha, here we will have gamma. And look, the sign of the derivative depends on this function, right? This function has two zeros, right? One is the negative 1, and one is 1, right? This is a quadratic function. And look, this quadratic function has negative coefficient, right? So it has its hands down. Okay, and look, out of this we can right away see that here the function derivative is positive. I'm sorry, here's derivative. Derivative is positive, which means that the function is increasing. Here we've got 0. So first function is increasing. We've got 0, right? Value of the derivative, and then derivative turns negative, which means that the function is decreasing. Even solely on that, we can conclude that this place must be a maximum. Of course, we have similar situation. However, we remember that we are not considering values of alpha that are negative. Okay, so look, we know that this is going to be a maximum, so we would expect to have a concave function, right? However, let's make sure that this is the case. Let's calculate the second derivative. So now we need to differentiate this expression, right? So again, we use the quotient rule, and with the quotient rule, we get 1, that this is 1 plus alpha to the power of 8. Then we've got derivative of the first expression. Derivative of the first expression over here is negative 8 alpha. Right? Negative 8 alpha multiplied by the expression in the denominator. And now we've got minus expression on the top, which is 4 times 1 minus alpha squared, and times derivative of this expression, which gives us 4 times 1 plus alpha to the power of 3, I'm sorry. And look, right away we can simplify everything. We can divide numerator and denominator by 1 plus alpha to the power of 3, so this is gone. This turns into a 5 and this turns into a 1. Okay, so let's carry on. So out of this we get that this is negative 8 alpha minus 8 alpha squared. Now, out of this one, we are getting that this is negative 16, right? And plus 16 alpha plus 16 alpha squared. It all is divided by 1 plus alpha to the power of 5. Now, can we simplify something? Well, not much. However, we see. We see that those two will definitely simplify. So we will have just 8x squared, right? So we've got 8x squared minus minus 8 alpha and minus 16 over 1 plus 1 plus alpha to the power of 5. Give me So if we're going to take 8 out, we're going to have x squared, I'm sorry, of course, alpha squared, minus 2 minus 2 alpha and minus alpha and minus 2. Now, divided, of course, by 1 plus alpha to the power of 5. Okay, and look, now again we need to just distinguish when is it bigger than 0, when is it smaller than 0. And look, we clearly see that as long as we assume that alpha is bigger than 1, is bigger than 0, this inside will definitely be always bigger than 1, taken to the power of 5, definitely positive. So look, the sign of this entire expression depends solely on the sign of alpha square minus alpha minus 2. And look, I need some new space, but again, this is a very simple quadratic equation. We see that the parabola here will have its hands up, right? Now we can easily rewrite it as minus a plus alpha minus 2 alpha, right? Minus 2 equals to 0, which gives us alpha plus 1 minus 2 alpha plus 1 equals to 0. So we get out of it alpha minus 2, alpha plus 1 equals to 0. So we get that alpha is equal to 2, or alpha is equal to negative 1. Okay, now what do we get from those two? If I'm going to draw it, this parabola, it's going to look like this. Okay, so here we will have 2, here we will have negative 1. Of course, again, we remember that actually nothing that is here interests us, because of course we are not considering alphas being lower than 1, right? Lower than 0. So, what do we get? Here, the second derivative is negative, right? When do we have negative second derivative? When the function is concave. However, it has an inflection point and then it becomes convex. So look, now we exactly know how to draw this situation, and let me draw it over here. Okay, so we're going to have a graph like this, where here is alpha, and here we got gamma. Right? What do we know now? Well, what we know is that if alpha happens to be 0, gamma is definitely 0, right? So our graph will start at this point. Of course, what is the highest value that gamma can take? Well, it is 1. Okay, let me just apply here. 1, right? And actually, it cannot even take this value, because as we've assumed, gamma know that 1 is dividing this area into 2 parts. Look, to the left of 1, function is increasing, and to the right of 1, the function is increasing, which we know that this point over here, I'm going to leave it open, would give us a maximum. Okay, now, from the second derivative, we know that the function first increases in a convex, is concave right up to 2. And then it is convex right after. Okay, so how can we now draw it? Look, first, this function is increasing in a concave manner. Then it reaches maximum and it starts to fall in a convex manner, concave manner. And then when it reaches value of 2, it actually starts to decline in a convex manner. Okay, when you will see this graph in your book, it's a little bit different. You know, they didn't care about this part. Without it, everything would look the same. However, they decided not to engage in this part. However, look, now we know every possible case. Look, if we are on this line, this line has, of course, the formula gamma equals 4 alpha over 1 plus alpha squared. If it happens to be that this condition is fulfilled, we will have repeated roots. Right? Now, look, if gamma is going to be higher than this, so if we are somewhere around here, if we are somewhere around here, we will have distinct roots. And finally, if we are below this line, so we are somewhere around here, what we are going to have are, of course, complex roots. And look, this is actually the main strength of this model. This model is extremely general. So look, within this model, we can clearly see that depending on a specific value of the parameters, we will have a different case. We can have distinct roots, repeated roots, or complex roots, and it all depends on what is the relationship between gamma and alpha. If it happens that gamma is bigger than this, we will have distinct roots. If they happen to be equal, right? Because remember, we are still using the same condition, right? They happen to be equal, we will have repeated roots. And if gamma happens to be smaller, we will have complex roots. Okay, and look, what we have done at this moment allowed us to distinguish between between three possible cases, and this is mathematically a very important distinction. However, of course, this is an economic model. And so the main feature that interests us is whether the equilibrium that we've calculated, so our y, p, so our both intertemporal equilibrium in an intertemporal and economic sense, is dynamically stable. So we need to now, of course, taking into consideration what we've already learned about these distinct cases, three distinct cases, we need to decide when we will have convergence, when we will have divergence, or maybe we will have neither. In this case, we will still have to consider, of course, different cases, different possibilities. We will go through them one by one. However, as you will see, they will all lead us to one condition for all three cases. Okay, so now we will assess convergence and divergence under different possible cases of roots. Okay, so we are concentrating now on convergence versus divergence because now we've already assessed when we will have different types of roots. Now, the only thing is to devise when under a given root we will have convergence or divergence. Okay, so let's start with case number one. In case number one, our a1 squared is bigger than 4a2. From the equation we've got is simply that gamma 1 plus alpha squared is bigger than 4 alpha gamma. Okay, and now look, if we're gonna have the first case, we're gonna have two roots, right? b1, b2 equal to negative a1 plus minus a1 squared minus 4a2 over 2, and this is equal to gamma 1 plus alpha plus minus square root of gamma square 1 plus alpha square minus 4 alpha gamma over 2. Okay, so those will be the roots. However, we need to establish some facts about it. And look, we can use a Viet theorems that we've reviewed earlier, when we said that b1 plus b2 is equal to a1, right? So we know that b1 and b2 is equal to gamma 1 plus alpha. Look, by assumptions, we know that this is definitely positive. Now the second Viet theorem was saying us that b1 times b2 was equal to a2, right? a2 is alpha and gamma times alpha, right? Again, we know that this is positive by assumptions. And look, what is this telling us? If the sum of two numbers is positive and the product of two numbers is positive, it means b1 and b2 must both be positive, right? We can have positive number as a product of two numbers if they are both positive, got positive, so definitely they have the same sign. And when you have two numbers with the same sign that are positive, they need to be positive. Okay, so look, right away, we've established quite a lot. We know that both roots are definitely going to be positive. However, divergence or convergence in this particular case will depend not just on the sign, but of course we need to know whether B1 and B2 are both between 0 and 1. Right? Only then we will have convergence. And to assess this, we're going to use a very simple trick. I'm going to do something like this. 1 minus B1 times 1 minus B2. Right? Let's calculate how much is that. Look, we get this is 1 minus B1 minus B2 plus B1 B2, which I can easily transform into 1 minus B1 plus B2 plus B1 times B2. Right? And look, again, I can just substitute the results we've obtained over here. And I'm going to rewrite them right away as well. So I'm getting that this is 1. And I'm going to expand that. We'll multiply everything up here. So this is minus gamma minus gamma alpha. And here we've got plus gamma alpha. Because those two clearly cancel each other out, all we've got is 1 minus gamma. How much is 1 minus gamma? Well, gamma is between 0 and 1. This is NPC, which means that this must also be between 0 and 1. Okay, look, why have we used this trick? Look, because if it would happen to be that, for example, B1 would be above 1, while the other one would be B1 would be below 1 and the other one, B2, would be above 1, we would have negative sign here, right? However, we still can see that this is not the case, because whatever we're going to get, it's going to be 1 minus gamma, so it's going to be between 1 and 0. Again, this is another example of the principles that we've deliberated on over here. Okay, so now look, knowing all this, when will we have a case like that? Because we definitely know B1 and B2 are above 0, right? We've already established that for sure. However, what we also know is that B1 is going to be bigger than B2. How do I know that? Well, in case of B2, B1, we add positive expression. In case of B2, we subtract. So of course we need to have it like this. Well, now we need to ask a question. When this is going to be lower than 1. Well, we will get definitely lower than 1, right? If B1 times B2 B2 is going to be lower than 1, right? So alpha times gamma would be smaller than 1. Okay, so look, let's summarize again. We know that they are both positive. We know that B1 is bigger than B2, and we can be sure that they're going to be below 1 if gamma times alpha is definitely below. But let's consider other possibilities. Look, what would happen if B1 would be equal to exactly 1 and B2 would be equal to also 1, right? Let's look what we would have over here. We would have 0 times 0, which is 0, right? We would have then 1 minus gamma equals to 0, or gamma equals to 0. So those results would imply gamma, equal to 1. But this is impossible. So those two cases can be rejected right away. Then, let's consider another possibility. What if B2 would be smaller than 0, right? Because we know that B2 is smaller. Then B1 is bigger than 0. But look, if we would have a situation that B2 that 1 and bigger and lower than 1. What would we have here? This is what we talked previously. If B2 is lower than 1, this is a positive number. If B1 is above 1, we would have negative number. We cannot get negative number over here. So this case is definitely impossible. So the last possibility we could have here is that 1 is lower than B2 and is lower than B1. Now, when would we have a case like this? Well, we would have a case like this. Again, if the product would be bigger than 1. So, alpha, gamma, bigger than 1. And look, this is actually giving us a formulation for when can we expect convergence and when can we expect divergence. So, under case number one, we will have convergence in convergence if alpha, gamma is bigger than 1, or equivalently, that gamma is bigger, then gamma is smaller than 1 over alpha, and we have divergence if alpha, gamma is bigger than 1, or equivalently that gamma is bigger than 1 over alpha. And look, this actually brings us to a more general point. And look, if we will be able to find line gamma equals 1 over alpha, this line will distinguish between two cases. The case of convergence and case of divergence. Okay, so now let's move to case number 2. And look, now that we know how to deal with the first one, dealing with the other two is going to be extremely simple. Okay, so in case number two, we've got, of course, repeated roots. So we will have just b equal to negative a1, a1 over 2, which gives us gamma 1 plus alpha over 2. Okay, what can I say about this result right away? Let me just write it also as. It's definitely positive. Again, by assumptions, we see that it is impossible to actually obtain a negative answer over here. Okay, now the question is, when is this going to be somewhere between 0 and 1? And look, let's again use a very simple trick. Look, what will happen if I'm going to say b to the power of 2? I'm going to get that this is gamma squared 1 plus alpha squared divided by 4. However, let's remember one thing. In case number 2, we've got that gamma squared 1 plus alpha squared is equal to exactly 4 alpha gamma. Which means that if I would divide both sides by 4, right? I would get this, which means that this expression is equal to alpha gamma. And look, now we have simpler case. We have 2 repeated roots. If 2 repeated roots which have the same value, they are both positive, then b squared is going to be between 0 and 1 only if the product is between 0 and 1, right? So we get from that this is going to be that b is going to be between 0 and 1 if and only if alpha gamma is lower than 1. And of course, it is going to be bigger than 1 if this expression is bigger than 1. So look, we've actually arrived at exactly the same conclusion. We can say that in case number 1 and in case number 2, we've got the same condition for convergence and divergence, and generally, as you see over here, it all depends on this function that we've got over here. Okay. So let's move on to case number 3, which, even though it's called complex, is definitely the easiest. Remember, we said that actually assessment of convergence properties of convergence, so of dynamic stability properties, in case of complex roots, is done by assessing R. And R alone, right? R is square root of A2, and this is equal to alpha E times gamma. Where this is going to be bigger than 0? When this is going to be bigger than 1? Again, we have a very similar situation as before. Look, R is going to be smaller than 1 if and only if alpha gamma is smaller than 1. R can be actually equal to 1 if it happens to be that alpha gamma is equal to exactly 1, and R will be smaller, it will be bigger than 1 if alpha gamma, I'm sorry, of course, 1 is of course bigger than 1. So actually here we've got 3 cases, because look, we can have convergence, we can have non-convergence, and we can have divergence. And it all depends on the same expression. So gamma equals 1 over alpha. And look, this is like a function y equals 1 over x. This is a simple hyperbolic function. It is extremely easy to draw. Okay, and this is what we're gonna do now. Okay, let's start with what we already found out. Look, first, we found out how whether the type of roots depends on the relationship between gamma and alpha. So if we have gamma over here, right? We have alpha over here. Yeah. Let's just say that we've got some 1. That is the highest value gamma can attain. We know that 1 is one of the interesting points, and 2 is one of a little bit less interesting points, but still interesting. Okay, so first, the first function that we were covering was gamma equals 4 alpha over 1 plus alpha squared. Well, this is the function that we've put here before, right? So that function was dividing the area into 3 parts. Everything below this line, complex above. Distinct roots on the line, repeated roots, right? We said that here we will have an inflection point. Okay. Let's do this line blue. Okay, then the second line we need to do is simply gamma equals 1 over alpha. So look, if alpha is equal to 1, gamma is equal to 1. Right? Again, we will be moving through this area. However, of course, here are the values that the function cannot take, and here are starting the values that are acceptable. Within our model. Okay, and look, now we will have a couple of different areas, each of which will be associated with different dynamic properties. singularities and different roots. Right? I'm sorry. Wrong. This is blue. Okay, and this is red. Okay. Now, let's analyze those areas, possible areas, one by one. Okay, let's start with what do we have in the yellow area over here. Well, what we definitely see in the yellow area is that that gamma is smaller than 1 minus alpha. Okay. So, what we have here is the situation where we have convergence, because here gamma over here, everywhere below this line, gamma is smaller than 1 minus alpha, right? So here, all this area below will have convergence. However, this part of the area is above the blue line. So what we see over here is that we will have an area where there's going to be, on one hand, convergence, but we will have no cycles, right? We will be going back to equilibrium smoothly, right? Because we have distinct roots. Okay, now let's consider this blue area over here with this orange dashes. Okay, what will we have in case of this area? Look, again, we are below the red line, which means we've got convergence. However, we will have repeated roots, right? So if we will have a case when we have blue with orange dashes, blue line with orange dashes, again we will have the same situation as here. So there will be convergence and no cycles. Okay, and finally we are dropping to this area over here. The green area over here is below the red line. We still have convergence, but we are going to have complex roots. So what are we going to have here? Look, we have convergence, but we have fluctuations. So in this part, in this particular case, we are still having convergence. However, we will have cycles. We will have damped fluctuations. Okay, so now I hope you see where I'm going with this further. Look, what will we have here? This area that you see over here is above the blue line, which means distinct roots. However, it is also above the red line, which means we will have divergence. So in this area that you see over here, we've we've got divergence and no cycles. Right, okay, so let me just pick, I'm sorry, but I'm slowly running out of colors. Okay. We will be using double colors. Okay. So now that we are on this line, so blue line with yellow, blue line with yellow dashes. Okay, here we are above the red line, and we have repeated roots. So along this line, so when we have the blue line with yellow dashes, we have divergence and no cycles. So finally, there are only two possible cases left. Of course, I would like to get more colors for that, but well, I don't. Okay. So look, now this area that you see over here, I would say, is above the red line, which means we have divergence, and we have divergence, and we have complex roots. Okay, I'm running out of place. I'm going to draw it over here. So what we have here is definitely divergence. However, here we should have stepped explosive fluctuations. So, even though here equilibrium is unstable, we have in business cycles, so fluctuations. Okay, and finally, the last is this line over here, right? So this is this one specific case where we would have no convergence, but also no divergence. So this is non-convergence. And of course, in this case, we will have uniform step fluctuations. Okay, I know this is quite a lot to take in at once. And you might probably be wondering, how instructive is this? Like, basically, what we did is that we took a very simple model and we distinguished between 7 different possible cases and what will happen in those cases. Now, this actually is an advantage of this model rather than disadvantage. Why? Look, this model is showing you that even when we introduce very simple dynamics into the national income model, we can produce business cycles. And if we can produce business cycles, it means we are reflecting in the model what we see in reality. And look, the thing is, even this very, very simple model can produce these different possible cases, and the only question remains, which of the cases is actually prevailing? And what does influences the prevalence of a given case? And let me check this question in turn. First, what is the case in which we have to do in reality? If you want to see what happens in the reality, all you need to do is to take the equation we were starting with in this video and estimate the econometry. Once you estimate the parameters, you can check if they follow these relationships, if they adhere. Based on the parameters that you will be able to estimate, you can check if these conditions are fulfilled. So actually, this is the advantage of the model, because it gives us all the possibilities, and if we are able to find the structural parameters through econometric estimation, we will be able to distinguish between one of these cases. Now, the second insight that is, to be perfectly honest, pretty clear, is that convergence of this model is negatively associated with the value of alpha. Of course, look, the thing is, we clearly see that from this equation, right? This equation is distinguishing between convergence and non-convergence. If it happens to be that gamma is bigger than 1 over alpha, right? So everywhere over here, we've got divergence. So it makes perfect sense that the bigger the alpha, so the bigger the value of the accelerator, the less stable the model gets. This is why it is so important in economic research to assess how companies react in their investment decisions to what customers are doing. Because if those decisions are very sensitive, we can be expecting that the economies will become very unstable. Okay, I believe that this is enough about Samuelson's model. In the next episode, we will do another economic application of second-order difference equations. This time, we will revisit Phillips curve model that we did previously. Okay, thank you for your attention. Take care.